Hi, my name is Kal Nayak, and this is my final project on HBase, a real-time column-oriented database. Here's an overview of my presentation. I'll start with a few slides to go over the technology of HBase. I'll give you a description of my project and the dataset I used. I'll go over my demo, which includes steps for software installation, pre-processing of the input data files, and HBase table creation. And lastly, performing the MapReduce jobs to obtain the results for my demo. I'll visualize some of the results and give you my conclusions. So what is HBase? HBase is a NoSQL real-time distributed columnar data store built on top of Hadoop's file system. It's an open source Apache project that's modeled after Google's Bigtable. It's capable of storing large quantities of sparse data by scaling horizontally. What does this mean exactly? HBase isn't a relational database. It doesn't speak SQL or enforce relationships within the data. It's column-oriented because it saves its data grouped by columns. Subsequent columns are stored contiguously on the disk. HBase saves its files typically in HDFS. HBase is designed to run on a cluster built using commodity hardware. HBase scales horizontally, and you can add more machines to the cluster. So why use HBase over RDBMS? HBase is schemaless. It doesn't have the concept of fixed column schema. At the time of table creation, we define only the column families. We don't define the columns or specify their types. All the rows in the table need not have the same columns. The data within HBase is stored as byte arrays. HBase is capable of storing structured and semi-structured data and can scale horizontally to store petabytes of data. It performs near real-time scans for overlap queries. It leverages the scalability, fault tolerance, and high availability provided by HDFS. What's the usage scenarios for HBase? HBase is best suited for random, real-time, read-write access of big data. Its column-oriented architecture allows for huge, wide, sparse tables without incurring any penalties. Its high write throughput makes it an ideal database for capturing incremental data coming from various data sources. It's built on top of Hadoop and inherits all of Hadoop's benefits. It can act as a source or a sink for MapReduce jobs and should be attractive to MapReduce users already invested in Hadoop's ecosystem. It's strongly consistent and uses multi-versioning to avoid conflicts caused by concurrent decoupled processes. It's even capable of retaining a history of changes. It can perform table scans in linear time and row key lookups in logarithmic order, or in some extreme cases, even constant order. HBase does have its drawbacks as well. It doesn't have a SQL-like query support, and its shell provides limited CRUD support in the form of gets, puts, deletes, and scans. There's no support for joins, and to overcome this, the data must be denormalized. If required, one would have to implement join functionality of their own outside of HBase. Atomicity is only guaranteed at the row level, and it doesn't support transactional feature that spans multiple rows or across tables. There's no innate support for secondary indexes, and support for this would have to be provided externally. Unlike traditional databases, it's not ACID compliant. Let's go over HBase's architecture. HBase follows a master-slave paradigm. Its main components are the master. The master is responsible for schema changes and other metadata operations like creation of tables and column families. It also assigns regions to region servers, and for this it takes the help of Apache Zookeeper. What's a region? Regions are essentially contiguous range of rows stored together. Each region is served by exactly one region server, and each of these servers can serve many regions at one time. Next, we have the region server. It's the region server who communicates with the client and handles data-related operations. It sends a heartbeat to the master. The Zookeeper. The Zookeeper provides services such as maintaining configuration information, naming registry for large distributed systems, and providing distributed synchronization. Clients communicate with regions via Zookeeper, the H file. The H files are typically saved in HDFS and provides a scalable, persistent, replicated storage layer for HBase. Memstore. The memstore is a write buffer for HBase, which accumulates data in memory before a permanent write. Its contents are flushed to a disk to form a new H file when memstore fills up. The write-ahead log or WAL. When a write is made, by default it goes into two places. The write-ahead log, also referred to as the H log, and the memstore. If HBase goes down and the data was not yet flushed to the disk from memstore, it can be recovered by playing the write-ahead log. Client API. A client may communicate with HBase using Java Client API or external APIs like Thrift, Avro, and REST. HBase has a simple data model. Tables in HBase are declared at schema definition time and are made up of rows which are lexicographically sorted by row keys. Data in tables is stored as byte arrays and there are no types. Rows are uniquely identified by row keys and can be arbitrary array of bytes that are not human readable necessarily. Row keys are the only form of indexing. Column families comprise of a group of columns and are defined at the time of table creation. Their names must be composed of printable characters. Columns are a part of column families and can be referenced by a column family and a qualifier. All the data in HBase is versioned with the help of timestamps, which are implicitly set by the system or explicitly set by the user for a column or a cell. A cell in HBase is identified by a combination of table, row key, column family, column, and timestamp. As a part of my project, I developed a demo. The goal of the demo was to use HBase to perform MapReduce jobs defined using Pig and analyze a big data set comprising of movie ratings from users. I wanted to extract user preferences based on demographic parameters such as age, gender, and occupation. The data was obtained from group lens datasets of movie lens users. It comprised of 1 million movie ratings for approximately 4,000 movies made by 6,000 users who joined Movie Lens in 2000. The data was obtained as 3 text files in that format for users, movies, and ratings respectively. HBase may be installed in 3 different modes: standalone, pseudo-distributed, or fully distributed. For the demo, I started off with my Yarn VM, which we've been using throughout this course. But the version of Hadoop doesn't matter, and you may choose an MRV1 version of the VM as well. I installed HBase in pseudo-distributed mode using yum. You first start off by installing HBase, followed by HBase master. You edit the HBase site XML file and add the configuration for distribution mode and root directory. You create the directory for HDFS. You install Zookeeper and followed by Zookeeper server and start the server. Next, you install HBase master, start it, install region server, and start it. Finally, you add HBase home to the bash profile and update the path variable. You may test the status of HBase by navigating to localhost and port number 610, or bring up HBase shell and type status. I installed pig using yum and added pig install, pig config, and pig class path to my bash profile and updated the path variable with pig install. The version numbers for pig class path depend on the version numbers of Hadoop, HBase, and Zookeeper installed on your machine. You may test the status of pig by bringing up the grunt shell. Here's an overview of the demo steps. I downloaded the group lens dataset and pre-processed them for MapReduce jobs. I created the HBase tables for MapReduce. I ran my MapReduce jobs in 3 phases. Phase 1 was to bulk upload the processed input data files into HBase tables. Phase 2 was to read the input from the HBase tables and determine the average rating for a movie genre based on demographic parameters. Phase 3 was to analyze the results from the previous step and determine the highest and the lowest rated genre for these parameters. Lastly, I analyzed the results stored in HDFS to determine the least and the most popular movie genre that appeared most frequently in the results. Processing the input files. The first step was to convert the DAT files to CSV format for MapReduce. From the user files, I retained all the columns except for the zip code. From the movies file, I retained the movie ID and the genres. From the ratings file, I retained all the fields except the timestamp. The next step was to create the HBase tables needed by the MapReduce jobs. There are 3 tables that correspond to the input, all of which have a single column family called data. Since we have 3 demographic parameters, namely gender, age, and genre, they can be combined in 7 unique ways, and we end up with 7 result tables. And once again, all these tables have a single column family called data. Next, we bulk upload the processed input data files into the input tables for HBase using MapReduce jobs defined using PIG. We read the input data from the input tables and create the average rating and the number of ratings for each genre based on demographic parameters. As an example, let's say we're doing this for demographic parameters of gender and age. In that case, we'll be computing the average ratings for all males and all females for all possible age buckets. The MapReduce jobs involve performing a join on 3 input tables followed by different combinations of group by on the demographic columns of the users. The results for these jobs are stored in the result tables. The last MapReduce job involves reading the input from the previous steps to determine the lowest and the highest rated movie genres for each demographic grouping within the table. The results for these jobs are stored in HDFS. I visualized some of the data within the result tables with bar graphs prepared using MATLAB. This is a graph for genre ratings grouped by age. As you can see, film noir is rated the highest and horror is rated the lowest overall. If you notice the graph, you'll even see that users over the age of 56 tend to rate movies higher than the other age groups, and users between the ages of 18 and 24 tend to rate movies lower than the other age groups. This is a graph for genre ratings grouped by gender. As you can see, once again, film noir is rated the highest and horror is rated the lowest overall. There's not much difference in the ways movies are rated by both genders, except for children's and musical genres, which are rated considerably higher by females. This is a graph for genre ratings grouped by gender and occupation. Once again, film noir is rated the highest and horror is rated the lowest overall. The only thing that stands out is that female lawyers rate documentaries considerably higher as compared to the other groupings within the graph. Here's my conclusions. By analyzing the results for my demo, I concluded that there were differences in the movie ratings across genres. Film noir was rated consistently higher and horror was rated consistently lower by most users. There were some other less prominent differences in movie ratings, when I grouped them by age, gender, and occupation. I was able to demonstrate the use of HBase and Hadoop to perform MapReduce jobs defined using Pig. My overall conclusions for HBase were that it's a system that's best suited for programmers and not data analysts. It's highly attractive to users already invested in the Hadoop ecosystem. It's built on top of HDFS and works seamlessly with Hadoop. I hope you take the time to explore my project in depth. Thank you for listening.